The next thing we're going to do is we're going to use permutations and combinations to calculate probability. In the last example that we did, example 1b, to calculate the number of arrangements of 5 books placed on a shelf, we used the calculation of 5 times 4 times 3 times 2 times 1. We had 5 books to choose from for our first spot on the shelf. Then after we placed that book, there are only 4, then 3, 2, 1, so on. When we see an expression that's written like this, there's a shorthand way of writing what that expression as a product is. It's written as 5 exclamation point. That exclamation point is read 5 factorial. 5 factorial represents this concept here. So if we want to do any kind of factorial, whether I do 4 factorial, that would be 4 times 3 times 2 times 1. Okay, so we would multiply that all out. That's 12 times 2, that's 24. They have defined 0 factorial to equal 1. And realistically, we don't do a lot of calculation of 0 factorial, but if we do, 0 factorial is equal to 1. Now we're going to make a distinction between permutations and combinations and use those to help us find probabilities in experiments or in situations that come up. So permutations and combinations, the fundamental counting principle, can also be used to determine the number of ways that n objects can be arranged in a certain order. So what's important to think about here is that we have n objects that we're going to arrange in a certain order. So order is going to make a difference. Just as in passwords, you can't turn your letters or numbers around, otherwise it won't recognize it and allow you in. An arrangement of n objects is called a permutation. Now, as soon as I say an arrangement, arrangement means it needs to be in a certain order, and that we have n objects to choose from tells us how many numbers, how many digits, how many people, how many books we can use to arrange. Whenever we use the word permutation, there's 2 things that you need to keep in mind. In a permutation, order is important. So order is a really big thing. Make sure that if you change the order, you automatically change the situation. This is another key point over here. In a permutation, the order of the object is important. If you have objects A and B, AB is different from BA. So we're saying as soon as we change that order, it becomes a different arrangement. Therefore, that's a permutation idea. The second thing that's implied is the objects may not be reused. So the objects cannot be reused. Now, in other language, we're saying there is no repetition of objects. So we can't repeat an object. Once the object is used, it cannot come up again and be used in the next sequence. So permutation is the big idea. Order is important. No repetition of your objects are allowed. In our key concepts area, it says the number of permutations of n objects taken n at a time is represented by n factorial. So this is the representation of a permutation of n objects taken n at a time. So you're going to use all the objects and put them in an arrangement, such as what we did here. We had 5 books. We were going to place all 5 books on the shelf, so we chose to use all 5 books taken 5 at a time. And that is nothing more than 5 factorial, which we've already done. What we can do, though, is sometimes we don't want to take all of the objects in our set. So the number of permutations of n objects taken r at a time is given by this. This is our permutation of n things taken r at a time. It's n factorial all over n minus r, in grouping symbols, factorial. What this is saying is we don't want to use every single member of our object set. We want to use a subset of them. So if we have 12 objects, maybe we only want to use 3. If we had 15 objects, use 14. So you'll see that in use coming in example 2. So permutation, order is very important. If you turn them around, you get a different combination, a different outcome, in that you cannot reuse objects once you've used it. So once you've placed a book on the shelf, there's no way you can use it again, as another example of that. So in example 2, we'll look at how we can apply our permutation concept to count how many and then eventually count and calculate probability. An alarm system requires a 7-digit code using the digits 0 through 9. If we use digits 0 through 9, we actually get to use 10 digits. So there are 10 objects in our set. For each digit may be used only one time. So we can only use them once, so there is no repetition. So I'm going to put no rep. How many different codes are possible? So there's a couple of ways of looking at this. A really intuitive way is to draw out 7 blanks. There's 2, 3, 4, 5, 6, 7. We're going to generate our code here by picking a number that has to fit in this location. Since we can't reuse them, we got to figure out how many objects we get to start with from the very beginning. From the start, we get to pick from 10 objects, but once I choose a digit or an object, we can't use it again. So then my second choice, in my second blank, I only have 9 objects left, and then it keeps counting down from there. So once I've chosen 2 objects, there's only 8 objects left, or 8 digits left. 7, 6, 5, 4. Now if we multiply these values together, we'll end up with our total number of possibilities that we can come up with, and that total is 604,800 outcomes possible. Now that's the intuitive way. Now we're going to look at being able to use our permutation formula. This is a permutation because there's no repetition and the order matters, so it's a permutation of, there's 10 objects, we want to choose 7 of them to create a code. So of the 10, choose 7 digits, which means in our calculation it's 10 factorial divided by 10 minus 7 factorial. Well, 10 factorial means we'd have to count down from 10, 9, 8, all the way down. I'm going to hold off on that just for a second. I want to calculate 10 minus 7, which is 3, so it's going to be 3 factorial. So in the denominator, I have 3 factorial. In the top, I've got 9, 8, 7, 6, 5, 4, 3, 2, 1, but 3, 2, 1 is 3 factorial. So we can represent 3, 2, 1 as 3 factorial, and these will reduce in our fraction. And what we end up with are the same set of numbers that we had kind of an intuitive sense in part A, but we still have our same 604,800 total outcomes that are possible. Question B piggybacks off of that. It says, if a code is randomly generated, what is the probability that the first 3 digits are odd? So to find the probability that the first 3 digits being odd, find the number of ways to select 3 odd digits and multiply by the number of ways to select the remaining digits, and then divide by the total possibility. In that little blip there, they're talking about the probability of any event happening. In general, to calculate probability, you have to figure out how many ways, what's the number of ways or number of favorable outcomes that are available, divided by the total number of possible outcomes. And these are favorable outcomes. So what we want to be able to do is we want to figure out what's the total number of favorable outcomes that are possible. Well, favorable outcome is if we have the first 3 digits, so first 3 digits odd. That's our first event. Our second event then, our next 4 digits, our last 4 digits, can be chosen however we want. Probability says we'll then figure out the number of possible outcomes. How many different ways are there to take 10 objects and choose 7? So this is our total possible. Okay, now this piggybacks off of question A. In question A, we figured out the total number of possible outcomes whenever we choose from our 10 objects, choose 7. So I'm looking at the denominator is, what's the probability or the permutation of 10 things taken 7 at a time? Well, we know that number is 604,800. What we have to calculate here is what's the probability, or what are the number of ways that we can choose the first 3 digits to be odd. So this is a permutation because, again, we're going to put them in order, and it's going to matter, and we want to make sure that all of our digits are odd. So of our set of numbers, we have the digits 0 to 9. There are 5 odd digits, and there are 5 even digits. And we want to make sure from those 5 digits that we have that are odd, we want to make sure that we select 3 of them. So of the 5 objects that are odd, choose 3. That's for event 1. This event 1 is going to guarantee that we have 3 odd digits in the first spot. Now, we also have a second event that has to happen, so this is event number 2. In event number 2, we want to make sure that we have 4 digits for our last spot. So permutation. the order in which you place them is going to make a difference, and once you use them, you can't use it again. So we got to keep in mind that we've already used 3 digits right here. Of the 5 odds, we chose 3. We took 3 out of this sample space, and once you use it, you can't use them again. So if we take 3 objects out of the 10, there's only 7 objects left. And how many of those do we need? We need to come up with 4 more digits. They might be odd, they don't have to be odd, but this is the calculation that we want to run in order to find our probability that the first 3 digits of this code will be odd if it's chosen at random. So now we got to do some calculations on this side. We want to calculate the probability of 5 things chosen 3 at a time. So we're going to come back to our formula. We got to do n factorial all over n minus r factorial. So this is n factorial, this is r factorial. So we got a 5 factorial all over 5 minus 3 factorial. Our second calculation for these, this is n, this is r. This is 7 factorial all over 7 minus 4 factorial. And the denominator, since we've already calculated this, I'm going to write it as 600n, I believe it was 4,800. I'm not going to do that calculation a second time. So on the numerator, it's 5 minus 3 factorial, it should have been, and in parentheses, 5 minus 3 is 2 factorial, so it's going to be 5 times 4 times 3 times 2 factorial all over 2 factorial times, this one is a 3 factorial, so I'm going to rewrite it as 7 times 6 times 5 times 4 times 3 factorial all over 3 factorial all over 604,800. The 2 factorials will cancel, the 3 factorials will cancel, so what I have to do is generate the numbers for multiplying 5 times 4 times 3. So 5 times 4 times 3 times 7 times 6 times 5 times 4. That's 50,400. So 50,400 for multiplying the numbers on top over 604,800. It'd be nice to put that lowest term. So in order to do that, I'm going to use my graphing calculator. I'm just going to take your 50,400 divided by 604,800. I'm going to convert it back into a fraction. So use your math key, change it back into a fraction. That equals 1/12, the lowest term. So there's a 1 in 12 chance, or about an 8.3% chance of this happening. So that's using the concept of permutation. Permutation order matters, and once you use it, you cannot use it again, so there's no replacement.